Hello AP Chemers. We're going to start chapter 17 today, which discusses aqueous equilibria, also known as buffers. But actually, chapter 17 is divided into three parts. The first part is buffers. Then after that, the second part is titrations. And the third part is solubility equilibria, or KSB. So we're going to start with buffers. And before we talk about buffers, we're going to talk about something called the common ion effect. That's where you have two substances that have a common ion between them, and you add those two together. For example, let's look at if we have a weak acid and its salt. So an example of a weak acid is HF. A salt that has the same ion as the weak acid would be something that has F- in it, so something like NaF. So this would be a weak acid and its salt, meaning that it has the ion from the acid. So let's say you take these and you put them both in water, and so the HF, since it's weak, it partially dissociates. You have an equilibrium to form H plus and F minus. We know that the Ka expression for this is going to be the concentration of H plus times the concentration of F minus over the concentration of the HF. So let's say that you take that HF solution, aqueous solution, and then you add some sodium fluoride to it, a salt that has a common ion. And so NaF completely dissociates, since it's a soluble salt, into Na plus and F minus. So there we see that there's a common ion. There's F minus here, and then also F minus there. Now when we add the NaF and it dissociates into these, the sodium ions don't really do much. They just sit there as spectators. But the F minus will contribute to this equilibrium because we're adding a common ion. So we're adding a product. Well, if you add a product, which way would this equilibrium shift? It's going to shift to the left to make more of that HF and use up some of the extra F minus that I have, and also use up some of the H plus. So let's write that down. The addition of F minus shifts the equilibrium to the left towards the reactant side. So let's look at all the concentrations in my reaction here. Let's start with the H plus. So since I am shifting my reaction to the left, I'm using up some of the H plus, and so that's going to decrease. Let's look next at the HF concentration. So we said that the equilibrium is shifting to the left side to make more HF, so my HF concentration will increase. And then my F minus concentration I am adding F minus, and so yes, I'm going to shift to the left to use up some of the F minus, but not all of it will get used up, and so the F minus concentration increases since I'm adding more of it. So that would be the effect on the equilibrium position and all of the concentrations of the species. What about Ka? What happens to the value of Ka? Well, remember that the equilibrium constant is a constant unless we change the temperature. The temperature is the only thing that's going to change it. So what would happen is this number goes up, this number goes down, the H plus. This number goes up, and this number goes up. The way that they increase or decrease will cancel each other out so that Ka remains the same because it's a constant it remains the same at the same temperature. So Ka remains the same. So another effect that we'll have is on the pH. So what do you think would happen to the pH? Well, the pH is the negative log of the concentration of the H+. Let's take a look at what's happening to the H+ concentration. The H+ concentration is going down. It's becoming less acidic. And so my pH would increase. Go up, meaning that's becoming more basic or less acidic. So adding a salt with a common ion to an acid will decrease its acidity, and so it will increase the pH. Next, let's try the opposite. Let's try a weak base with its salt. So a weak base, an example of that is NH3, ammonia. And so a salt that contains a common ion would be ammonium nitrate. So let's look at the dissociation of our base first. It's a weak base, so we have an equilibrium. You can maybe add H2O here if you'd like. And that would form NH4 plus and OH minus. And then if you add the ammonium nitrate, that is a soluble salt. So it dissociates 100% into NH4 plus and NO3 minus. And so here we have our common ion. Both are giving off NH4 plus. So let's look at how that would shift the equilibrium for our ammonia here. So if I'm adding more NH4 plus, the reaction or the equilibrium will shift to the left again. So it would produce more ammonia, use up some of the extra NH4 plus that I added, not all of it, so that would still increase. It's also going to use up some of the hydroxide ion. So let's write that down. So your NH3 concentration, well, let's say the equilibrium shifts left. Our NH3 concentration would increase. Our OH minus concentration would decrease, again, so it's shifting to the left. And then our NH4 plus would increase because I'm adding more of it. Yes, it does shift to the left, but I did add more of it. Not all of it would get used up, so it's going to overall increase. Let's look at the effect on the pH. And so my hydroxide ion is going down, so it's becoming less basic, and so my pH would go down since it's becoming less basic. So adding a salt with a common ion to an acid makes it less acidic. Adding a common ion to a base makes it less basic. Now we had a similar chart to this one right here on our last chapter. We had most of these on here, and so we said if I'm going from most acidic to most basic with neutral in the middle, so the most acidic would be, again, if these were all the same concentration, would be strong acids, the 6 strong acids. Then if I have weak acids, we're going to add this now. So if I have a weak acid with its conjugate base, meaning really a weak acid with its salt, like for example, an HF is a weak acid, F minus would be its conjugate base or its ion or its salt. So if you have a weak acid and its conjugate base or a weak acid and its salt, that would be a little bit less acidic than if you had just the weak acid by itself, because remember, it drives it to the left, making it a little bit less acidic. Then you'd have the salts, so you'd have the acidic salt, then the neutral salt, and then the basic salt. And then on the basic side, the most basic would be the strong bases, followed by weak bases, followed by weak bases with their salts, or weak bases with their conjugate acids. That means the same thing. Like, for example, NH3 and NH4Cl. So the NH4 plus would be the common ion there. So those would be a little bit less basic than weak base, but more basic than a salt. So this chart kind of is helpful to determine acidity and basicity of different substances. All right, let's try a problem where we have one of these acids and its salts and do some calculations with them. So here's an example. It says that I have a solution of 10th molar acetic acid and 0.2 molar sodium acetate. So the acetate ion here would be our common ion, right? Because acetic acid dissociates into H plus and acetate. So the sodium acetate would be the salt of this acid, or you can think of it as the conjugate base of this acid. Same thing. So we have a mixture of acetic acid and sodium acetate. We want to know what is the pH of the solution of just the acid by itself, and then what is the pH of the solution when you add the common ion to it, so the mixture. So let's start with just the acid by itself. So only the acid. So we know how to do this from last chapter. We would write our acid dissociation equation. And so that dissociates partially into H plus and acetate ion. We're going to do an ice chart. Initially, the acetate ion is 10th molar. These are 0 and 0. We're going to say that's minus X, plus X, and plus X. So 0.1 minus X, X, and X. Then we're going to set up our Ka expression. So the Ka expression is equal to the concentration of the H plus times the concentration of the acetate ion divided by the concentration of the acetic acid. All right. The Ka value, you would look that up. For acetic acid, we've used it so much, you might have it already memorized. Not that you would need to. It's 1.8 times 10 to the negative fifth. That is equal to X times X over 0.1 minus X. And plug that into your calculator. You get that X is equal to 0.00133 molar. Those are threes there. Kind of hard to read. Our X here is our H plus concentration. And so if I wanted the pH, I would just take negative log of that. And so that ends up being 2.86, which makes sense. It's a weak acid, so it should be pretty acidic. Now, let's take a look at what if I have the acid plus the salt, or plus its conjugate base. So what I like to do is I like to write the salt dissociation first before my acid or my base. So I always start with my salt. So like our last chapter, we'd write NaCH3COO. Since that's a soluble salt, that goes 100% into Na plus, and then the acetate ion. And then I, after that, would write my acid or base dissociation. In this case, I have acetic acid, so CH3COOH. Then that's an equilibrium. It dissociates into H plus. That's a plus there. And acetate ion. So my common ion here is my acetate ion. I'm going to do an ice chart. So there's my ice. Initially, my acetic acid is 10th molar. Initially, my H plus is 0, but my acetate in this case is not 0 like this one, because I have some acetate that's coming from that salt. And so I know that that salt is 0.20 molar, and it goes 100% to completion, so that means this is also 0.20 molar, and this is also 0.20 molar. And so before any dissociation of my acid, before any of this dissociates, I have still some acetate from the salt, and I have 0.20 molar of that acetate. So that is going to be my initial for this one here, 0.20 molar. And then the rest of it is the same. This is minus X. Some of this will dissociate. It's going to form some H plus and some acetate. So this is 0.1 minus X, X, and 0.2 plus X. And I'd set up my Ka expression the same way. So 1.8 times 10 to the negative fifth. That was my Ka still for my acetic acid. That is equal to my H plus concentration. So X times the acetate concentration, so 0.2 plus X, over the acetic acid concentration, so 0.1 minus X, and then I'd solve for X. Now let's make a prediction. So I have a weak acid, which is my acetic acid. By itself, the pH is 2.86. If I were to add some of the conjugate base to this, so some acetate, it's going to make the reaction shift to the left side. So I'm going to have less H pluses, which means it's going to be less acidic. So my pH should go up, should be more towards the basic side or less acidic. So let's actually calculate that. If you plug it into your calculator, you get that X here is 9 times 10 to the negative 6 molar. So that's a much lower number than my X was here. And in this case, X again is my H plus concentration. So if I wanted the pH, it's just negative log of that, which ends up being 5.04. That's a big jump here from 2.86 to 5.04. Definitely made it less acidic. So why are we talking about these common ions? Well, because that's what makes buffers. So let's define what a buffer is together. A buffer is a solution that resists or opposes a change in pH when extra H plus or OH minus ions are added. So for example, if I have distilled water and it's a pH of 7 and I add like a couple of drops of HCl, the pH drops dramatically to maybe 1 or 2. Or if I take my distilled water with a pH of 7 and I add a couple of drops of NaOH, it would jump dramatically to like 13 or 14 or something like that. If I were to take a buffered solution as opposed to water, and let's say my buffered solution is a pH of 7, if I were to add an acid to that, the pH would remain about 7. Or if I were to add a base, the pH again remains about 7. Now, a buffer does not need to hold the pH at 7. So some buffers are acidic and some buffers are basic. Whatever the starting pH of the buffer is, that pH remains constant. It does not change, or it changes very, very little. So it's a solution that will minimize any changes in pH when you add H pluses or OH minuses. It does not necessarily have to hold it at a pH of 7. So if my buffer starts out at pH 11 and I keep adding acid to it, it should remain pretty close to 11 until a certain limit. Now, a buffered solution is made of a weak acid and its salt or a weak base and its salt. So a buffer solution is actually a mixture of two different substances mixed together in water. You have to have a weak acid and its salt or its conjugate, or a weak base and its salt or its conjugate. So weak acid with its salt or weak base with its salt. Not just one by itself, but two things. And so a weak acid and its salt have a common ion, or a weak base and its salt have a common ion, and that's the whole point of talking about common ions to start this chapter. So let's try a problem here. It says I have lactic acid buffer. So that means it's made of lactic acid and it's salt and something that has lactate ion. And so I make it by using 1 molar lactic acid and 1 molar sodium lactate. Again, a buffer has to be those two substances together. Weak acid and its salt, or weak base and its salt. They give us the Ka for lactic acid, and they want us to find the pH. So, like I mentioned before, whenever you have a salt and an acid or a base, I recommend that you write the dissociation of the salt first. So I'm going to go ahead and do that. So I have sodium lactate. Now, if you know what the formula is, that's great. If you don't, remember you can abbreviate it. So I'm going to use Na-lac as my lactic acid. As my sodium lactate. That is soluble salt because it has sodium ions in it. It dissociates 100% into Na plus and lactate ion. Then I'm going to write my equation for the dissociation of the lactic acid itself. So I'm going to call it H-lac, and that's an equilibrium that forms H plus and lactic ion again. Sorry, not lactic ion, lactate ion. So my lactate ion is my common ion. I want to find the pH, and this is an equilibrium here. This lactic acid is weak, so there's an equilibrium. So I'm going to do an ice chart. So, all right, ice. Initially, my lactic acid tells me that it's 1 molar, so I'm going to put that in. Initially, I don't have any H pluses. I don't have any lactate ions from the dissociation yet, but I do have lactate ion from the sodium lactate. It tells me that my sodium lactate is 1 molar. So this solution is 1.0 molar. Since it goes 100%, that means this is 1.0 molar. And this is also 1.0 molar. And so my initial here is 1.0 molar. And I do it the same as always. This is minus x plus x plus x. So 1 minus x, x, and 1 plus x. I set up my Ka expression. It's the concentration of the H plus times the concentration of the lactate ion over concentration of my lactic acid. Our Ka is 1.4 times 10 to the negative 4th. That is equal to x times 1 plus x over 1 minus x. I solve for x. X ends up being 1.41 times 10 to the negative 4th molar. And that x is my H plus concentration at equilibrium. And so if I want the pH for the solution, it's just negative log of that, which ends up being 3.85. So we already did a problem similar to that earlier on the page. We just didn't call it a buffer. Here we have an acid and its salt. We did it the same exact way as the buffer. So that's how you find the pH of a buffer. And remember that a buffer does not need to have a pH of 7. This buffer is acidic. If it's going to be a weak acid with its salt, obviously it's going to be acidic. If it's going to be a weak base and its salt, obviously it's going to be basic. So in this case, it's an acid with its salt, so it's going to be acidic. And so this buffer system will hold the pH at 3.85, or pretty close to that. All right, so here we're going to look more at what a buffer does, how it resists the changes in pH. So we're going to start by calculating the pH for just some acid in water. It's not buffered, obviously. Then we're going to look at the pH of just a buffer in letter B. And then in C, we're actually going to look at how if I were to add the acid to the buffer as opposed to add the acid to the water, how is that buffer going to resist changes to the pH? So let's start with the very first one, A. we're going to add a milliliter of HCl and see how it's going to change the pH of water. We know that the pH of just pure water is going to be 7. And so now let's just try to add a milliliter, just 1 milliliter, of 1 molar HCl to it. So HCl is a strong acid, and so if I want to write the dissociation for HCl, since it's strong, it goes 100% to completion, no need for an equilibrium there, to H plus and Cl minus. I have a milliliter of 1 molar, and so I can figure out how many moles that is. So 0.001 liters times 1.0 molar is going to be 0.001 moles. That's of HCl. And so if I know this is 0.001 moles, then I know this is also going to be 0.001 moles. Same thing for that one. And so I have 0.001 moles in my water. So the concentration of the H plus is going to be 0.001 moles of H plus over my volume. My volume is, I have a liter of water and 1 milliliter of the acid, so 1.001 liters. And so the concentration ends up being 9.99 times 10 to the negative fourth. So if I want the pH for that, it's negative log of that number, which would be pretty much 3.0. Okay, so if I take just pure water, pH of 7, and I add 1 milliliter of that acid, it drops my pH to 3. Now from 7 to 3, that's 4 difference. That's what, 10,000 times the difference in the H plus concentration. It increases by 10,000 times. All right, now let's look at letter B. So letter B, we're just going to look at a buffer system. I'm not adding an acid or anything to it, just a buffer system. So I want to calculate the pH of a buffer that's made of 1 liter of acetic acid and sodium acetate. And it gives us the concentrations of the acetic acid and the sodium acetate in that buffer. So that's like the previous problem that we did, not this one, but the one from the previous page. So I'm going to set up my dissociation of my salt first. So NaCH3COO. That 100% dissociates into Na plus and the acetate ion. Then I'm going to write my dissociation for the acetic acid, CH3COOH. That's in equilibrium. Dissociates into H plus and the acetate ion. I want the pH for this, and this is in equilibrium, so I'm going to set up an ice chart. Initially, the concentration of my acetic acid is 0.70 molar. Initially, my concentration of the H plus is 0, but my acetate, I have some acetate coming from the sodium acetate. The concentration of the sodium acetate, it tells me, is 0.60 molar, and so this is 0.60 molar. Some of the acetic acid is going to dissociate, so minus X plus X plus X, 0.7 minus X, X, and 0.6 plus X. My Ka expression is going to be the concentration of the H plus times the acetate over the acetic acid. Let me write that down. My Ka value is 1.8 times 10 to the negative fifth. That's equal to X times 0.6 plus X over 0.7 minus X. X ends up being 2.1 times 10 to the negative fifth. That's my H plus concentration. My pH is negative log of that. which is 4.68. And that's just my buffer by itself. Let's take a look at part C. So now in part C, what I'm going to do is I'm going to calculate the pH when the acid in part A, so that HCl, that 1 milliliter of the HCl, is now going to be added to the buffer in part B. So, let's think about what's happening here. So I have a beaker that has a buffer. The buffer is made up of my acetic acid, so CH3COOH. And it also has some sodium acetate. The sodium ions are negligible, they're spectators. What I care about here is my acetate, that's my common ion. Okay, now again, a buffer is made up of an acid and its conjugate base, or a base and its conjugate acid. So any buffer has an acidic portion and a basic portion in it. Now, I'm going to add some HCl to it, so I'm adding some acid to it. So now I'm going to add H pluses. Now, if I add H pluses to this buffer system, since the buffer has an acidic portion, so my acetic acid is the acidic portion, my acetate ion is my conjugate base. If I add acid to this mixture, would my acid, my H pluses, react with the acidic portion or with the basic portion? Well, if I add an acid reacts with a base. And so my H pluses are going to react with my acetate. Let's say I add some OH minuses. If I were to theoretically add OH minuses, then what would they react with? They would react with the acidic portion. So an acid reacts with a base reacts with an acid. And so in this case, I'm adding H pluses, so it's going to react with the conjugate base. Let's write the reaction that would result from here. So my reaction would be between H plus and the acetate ion. When these react together, and these are reactions that go to completion, by the way, any acid-base reaction goes 100%, almost 100% to completion. If you have a base dissociating or an acid dissociating, that's an equilibrium. But if you take an acid, react it with a base, that usually goes almost 100% to completion. So that would form what? It would form acetic acid. So if I want to find the pH for this, what I would do is first I would figure out how many moles did I start with, and how many moles changed, and how many moles do I end with. So I'm going to do an ice chart, but I want you to be careful that this is not really ice as in equilibrium, because that's kind of like a reaction that goes to completion. So I'm going to call it end as opposed to equilibrium as my I there. Or sorry, as my E. So initially, how many moles of H plus did I have? Well, if we look back at our problem here, I had 0.001 moles of H plus. So I'm going to put that into my table here. So 0.001 moles. Okay, let's look at my acetate. So my acetate comes from the sodium acetate here. And I'm going to erase a little bit of this so it's not as crowded so I can see it. So my acetate, I have 0.60 molar, and it's a 1 liter. And so that means I have 0.60 moles, right? So I'm going to put that in. That's 0.60 moles. And then let's look at my acetic acid initially. My acetic acid, the concentration was 0.70 molar, and I have a liter of it, so that's 0.70 moles. So I'm going to write 0.70 moles. So that's how many moles of each of my species I have. Let's figure out what the change would be. Now, we said this is a reaction that pretty much goes to completion. And so in this case, 5.60 moles of the acetate and only 0.001 moles of the H+. Which one is my limiting reactant? Well, H+ is my limiting reactant. After 0.001 moles of it is used up, it's done. I have a whole bunch of acetate, but it's just going to sit there. So my limiting reactant is the H+. I have 0.001 moles of it, so that's how much is going to get used up, because by definition, a limiting reactant gets used up. So my change is going to be minus 0.001 moles for this one. Since this is a 1-to-1 ratio, and acetate is also a reactant, that means I would use up 0.001 moles of this as well. And since it's a 1-to-1 ratio and I'm forming the acetic acid, that means this change is going to be plus 0.001 moles. The net at the end, so this is the end as opposed to equilibrium. For my acid, I have 0.001 minus 0.001, so I end up with 0 moles. You should always end up with 0 moles for your limiting reactant. Then 0.60 minus 0.001 is 0.599 moles. And my acetic acid, I end up with 0.701 moles. So after my reaction here, remember I had my beaker that had my buffer system, and I added H+, so the H+ reacted with the CH3COO minus. This is what I end up with after that reaction. Okay? Then what I do next is I calculate now the pH like I normally would by the dissociation of that acetic acid buffer system. So I find the pH of the buffer system just like I did in part B here. But instead of using these as my initial concentrations, now these are my initial concentrations. So let me try to do that. So you want to rewrite your dissociation equation for your acid. So CH3COOH, that's my acid and my buffer, dissociates into H+ and CH3COO minus. So I do it just like I would find the pH for any buffer. I do an ice chart. But now my initial are these concentrations. So my acetic acid is 0.701. And you can do this in molar or moles. It doesn't really matter. Let me do it in moles because it's just easier. H+ is 0. And this is 0.599 moles. Minus X plus X plus X, 0.701 minus X, X, and 0.599 plus X. You know what, actually, I would use maybe molar concentrations for these instead of moles, because I need to set it up to my Ka expression, so that needs to be molarity. So I'm going to fix that real quick. This is 0.701 moles, but it's divided by 1.001 liter, because remember, I have 1 liter in my buffer and 1 milliliter from my acid. So let me fix that real quick. So this would actually be 0.7. I'm going to erase these. Sorry about that. So I'm going to go ahead and divide this by 1.001 liters and this by 1.001 liters. This ends up being 0.598 molar. This is 0.7003 molar. So those are the concentrations that I'm going to use. So 0.7003 molar, 0.598 molar, minus x plus x plus x, 0.7003 minus x, 0.598 plus x. So now I can set up my Ka expression. So my Ka is equal to 1.8 times 10 to the negative fifth. That is going to be x times 0.598 plus x over 0.7003 minus x. Let's solve for x. X ends up being 2.11 times 10 to the negative fifth, which is my H plus concentration, so pH is just negative log of that. That ends up being 4.68. So let's look at that. My buffer, by itself, its pH is 4.68. I add a milliliter of acid to it, it remains at 4.68. It did not change. Whereas my distilled water started out at a pH of 7, and then when I added that same milliliter of acid, it changed to 3, 10,000 times more H+. So that buffer seems to be effective for that amount of acid. All right, my part D is not showing up, so I wrote it out real quick. So part D says to calculate the pH, 100 milliliters of 1 molar NaOH is added to that same buffer in part B. So let's look at our beaker now. My beaker has some acetic acid. My buffer is made up of acetic acid and of some acetate ion. And now I'm going to add some NaOH, which is really OH minuses. All right, so whenever you have a buffer, again, it's made up of an acidic portion and a basic portion. So when you're adding acid or base to it, by the way, this is not going to be asked of you on the AP exam to calculate when you add an acid or a base to a buffer, but you do need to know that for my test. So anyway, a buffer has an acidic portion and a basic portion. That's my buffer right here. I'm going to add some OH minuses. Well, OH minus is a base. Guess what it's going to react with? Yep, it's going to react. Since that's a base, it's going to react with the acid. So the first thing you want to do is write out the reaction between the acid and the buffer, the acid and the base, the buffer with your extra OH minuses. So let's write that down. So my CH3COH portion of my buffer is reacting with the OH minus. Guess what that's going to produce? And remember, that's just the one arrow. Well, let's see. The acid is going to give off an H plus to the OH minus to form water, and I'd form acetate ion. So I'd form CH3COO minus and water. Remember, when you are adding an acid or a base to the buffer, first thing you want to do is write out how many moles of each species you had and how many moles you used up. And remember, this is end as opposed to equilibrium. So my acetic acid, I said, is going to be 0.700 moles. My base, let's see, I have 100 milliliters of 1 molar, so 1 moles per liter times 10th liters, so that's 0.1 moles. My acetate, we said from the previous problem, is 0.600 moles. My water, I don't care about, it's a liquid. So I look to see which one is limiting me, which one's lower, since they're 1-to-1. Looks like my hydroxide is limiting me. And so I'm going to use up 0.1 moles of the hydroxide. So my change is going to be minus 0.1 moles here. And it's also going to be minus 0.1 moles here. And here is going to be plus 0.1 moles. So at the end, this is 0.6 moles. This is 0, and this is 0.7 moles. I'm going to go ahead and divide by the total volume so I don't forget like last time. Let's see, my total volume, I have a liter of the buffer and I have 1/10 liter of the base. So my total is 1.1 liters. This is going to give me 0.54 molar. It's going to be 0 molar, and this is going to be 0.63 molar. So now I set up an ice chart for the dissociation of my buffer. My buffer, remember, was this. So it's an acid and its conjugate. So I write my acid dissociation equation. H plus acetate, ice chart, and I start with these concentrations. So 0.54 molar, 0.63 molar, minus x plus x plus x, 0.54 minus x, x, and 0.63 plus x. My Ka is still 1.8 times 10 to the negative fifth is equal to x times 0.63 plus x over 0.54 minus x. My x, which is my H plus concentration, ends up being 1.54 times 10 to the negative fifth molar. And so my pH ends up being 4.81. Let's look at this. So my buffer by itself, let's look back at B. My buffer by itself had a pH of 4.86. I go ahead and add 100 milliliters of 10th molar NaOH. That's pretty strong. That's a lot. And I only go to 4.81. From 4.86 to 4.81, that's not too bad. So that's pretty good. From 4.868 to 4.81. Changed by a little bit, but not a lot. So let's review. If you wanted to find the pH of just a buffer by itself, like we did in B, you write out your salt, you write out your dissociation of the acid, you do a regular ice chart, and that's it. If you wanted to add an acid or a base to your buffer, what you do is you look at your acidic and basic portion of the buffer and you check the extra acid. What do you react it with? An acid will react with a base, and a base will react with the acid. Then you write out the moles of each of your substances, what you start with, what the change is, you figure out what you want to use your limiting reactant, and then what's left, divide by the total volume to get your concentrations, and that's what you use for your ice chart for your buffer. Next time, we're going to learn about the Henderson-Hasselbalch equation, which actually saves a lot of work. It's a shortcut for doing these ice charts.